So we're going to start the derivatives info. Okay. So derivatives part one, the product and quotient rule. So in the last lesson, we defined what a derivative was of a function. Here it is again. The derivative of a function f with respect to the variable x is the function f prime, whose value at x is given by this expression, this limit, provided the limit exists. Always remember that little bit at the end there. Okay. So what we're going to do now is I'm going to start showing you how this different techniques that we can use to help us find this derivative analytically without having to go through the limit. Okay, so the limit definition is important. It will be on your AP exam and other exams, but now we're going to condense these rules down and look at the rules that you're going to use to find the derivatives from this point forward. Well, we're going to learn some rules that were derived from this definition up here that will make finding the derivative function more efficient. So we are going to look at some rules here. First one, the derivative of a constant function. So if I have a function f of x equals to c, which is just a number, so it's basically a horizontal line, where c is a constant, then the derivative of that function with respect to x, this is how you would read it, the derivative of f of x with respect to x is the derivative of the constant with respect to x, which is equal to 0. So the derivative of a constant is literally 0 because this is a horizontal line. And since the derivative represents the slope of a tangent to a curve, and the curve happens to be a horizontal line, the slope of a horizontal line is indeed 0. And then I showed you through the limit definition how that comes about. So the derivative represents the slope of the curve at any point, and a constant function is a horizontal line with a slope of 0. So this just confirms things that we already know. Okay. Let's look at another rule. It's called the power rule. Okay. The power rule is anything to the n power raised to an exponent. Okay. Let's get a little bit better focus here real quick. Okay, so I have some function to a power. N is a real number. U is a differential function of x, and it does not equal 0. So this is just a generic placeholder for a function of x because this is a function of x. See, there's a variable x here. So what does the rule say to do? So look closely at it. The derivative of u to a power of n with respect to x, the exponent is multiplied out to the front, so n drops out in front, and then you lower the exponent by 1 on that expression. And then don't forget that you also have to take the derivative of that expression with respect to x. Okay? Because u is a function of x, we need to multiply by its derivative also. This concept is the chain rule, and we're going to explore this in more detail later. I want you to learn the rules in their final form. So in other words, some textbooks, your textbook is one of them, it will show you this rule with just like x to an n, where this function is x. But the advanced rule, the rule you need to memorize, is this one right here. So I gave it to you in its final form instead of making you memorize two different forms. I didn't want any confusion on that. So when you're having quantity to a power, you multiply the exponent out in front, lower the exponent by 1, and then take the derivative of the function u, whatever that may be. We'll talk more about that as we explore. To use the power function rule, we must first be able to recognize when we have it. Okay, so we have to be able to recognize when we have the power rule. So here's an example. Nope. Let's just take a look right here. Move it here so you can see the whole question. Which of the following are power functions? In other words, which one of these can I use this rule on? So again, let's go back to the rule. It is some function of x raised to a power, and that power is a real number. So we look at these and say, okay, does any of these down here satisfy that condition? All right. Can I rewrite these in some fashion? Well, the exponent has to be a number. So looking at these right here, we can see immediately that this one is not going to work because this exponent is a variable. And this one is not going to work because this exponent is a variable. This doesn't look like something to a power, but can I use any of our previous, properties or rules that we've learned before to look at this differently? And the answer to this one is yes, I can. This is 1 over x, but if I use exponent rules, I can rewrite this as x to the negative 1. And so now I have a function of x raised to a number power. And so yes, this one here is a function that I can use this rule on. This is another one. A square root is a fractional exponent. So here's my function of x, and here is my numerical exponent. This one is a little bit more challenging, and basically because it was a piecewise function, you cannot do this one in a power form. You have to use, it has its own rule that we'll look at later. So you can see that's what I had written down here. No, 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 and these two are yeses. So be aware that you're going to need to look at these things and see if you can put it into a power form to use that rule. This is one of your major rules right here. So let's look at an example that I have over here. Find the derivative function for each function given. So instead of using the limit definition, which is what we would be doing, we're going to do this using the two rules that we have got, okay, if we can. So the first thing is, it looks like we're going to be doing, most of these looks like powers of x's, okay, functions of x. And so is this x to a number power? If the answer is yes, then we can do and find the derivative. And because this is a function notation, you may use the f prime notation to represent the derivative. So the derivative of f with respect to x would be, take the exponent, multiply it out in front, times this thing and lower the exponent by 1. So this is going to be 5 minus 1 is 4, times, and then what's the derivative of that? What is the derivative of x with respect to x? Well, if you look closely at it, dx divided by dx is simply a 1, correct? And so this right here becomes our derivative. F prime of x is simply 5x to the 4th. And there you go. This one right here, this is not in power form, but I know I can put it in power form. So I'm going to rewrite this as x to the 1/2 power. And now I'm going to use the power rule. So g prime of x, take the exponent, 1/2, multiply it out in front. Take this quantity, whatever it is, this thing to the power, that expression gets rewritten, and then I lower this exponent by 1. So 1/2 minus 1 is a negative 1/2. And then whatever that is, take the derivative of it with respect to x. This here I can clearly see is going to be a 1. So my g prime is going to be 1/2 x to the negative 1/2. And for now, we can leave it just like that. And we can continue on. Here is h of x is x to the e. E is indeed a number. So we can use our rule for it. So h prime of x, take the exponent, multiply it out in front. There's my base number right here, my x quantity. And then lower the exponent by 1, which basically means take the e and subtract 1 from it. Then we have to multiply by this quantity, the derivative of that quantity with respect to x. And again, we can see there's going to be a 1. And so this becomes e times x to the e minus 1. That is what that is equal to. since you don't know what E is exactly, you just leave it in that format right there. What about if I have a different variable? Does that change anything? Absolutely not. You just use the problem, the same techniques with this new variable. Everything's exactly the same thing. This is already in a power form. So K prime of T is 7 over 6 times T. Lower this exponent by 1. So 7 over 6 minus 6 over 6 is 1 over 6 times the derivative of T. Because the variable was T to start with when I took the derivative, it's the variable of this, the derivative of this, with respect to T, because that was the variable we started with. And so we get 7, 6, T to the 1, 6 is our derivative. These two are very similar in nature, okay? So this right here is basically going to be rewritten as x to the negative 3, okay? So what is m prime of x? Take the exponent, multiply it out in front, take the quantity, lower the exponent by 1, so a negative 3 minus 1 is negative 4, times take the quantity, then take the derivative of that quantity with respect to x. That becomes a 1, negative 3, x to the negative 4. Now, sometimes they will take this negative exponent and write it in a positive exponent form, which means this can become negative 3 on top, x to the positive 4 on the bottom. Any one of these two forms is agreeable, okay? And this one is exactly the same process, except for you're going to rewrite p of x as x to the negative 1. And you just do the same process here. So what is p prime going to be? Is going to be a negative x to the negative 2 dx, or a negative 1 over x squared. Okay? So there's that. Let's look at another example that I have here. So f of x is x squared. Excuse me, you can't see that. F of x is x squared. Use the limit definition of the derivative to find f prime at negative 1. Okay? So for this one, I'm going to use the alternate form. I'm going to use the alternate form for this. I'm going to use the limit. I'll put right here. Remember, the alternate form was the limit as x approaches a, f of x minus f of a, x minus a. I'm going to use that form for the derivative. So this is f prime of a. So for that solution, I'm going to use the limit as x approaches negative 1 of f of x minus f of negative 1, because that's what I want to find, over x minus a negative 1. My fault here, guys. Right here in the front, put f prime of negative 1 equals right in front of that. Okay? So then we work this out. So this is going to be the limit as x approaches negative 1. This will be x squared minus 1, because plug in negative 1 in here, you're going to get positive 1, over x plus 1. Using the factoring technique on top, you're going to get the limit as x approaches negative 1. This will be x plus 1, x minus 1, over x plus 1. It will reduce, giving me the limit as x approaches negative 1 of x minus 1. And then if I plug in using direct substitution, plug in negative 1 in here, I'm going to get negative 2. So that's using the limit definition to find the derivative at a point. Part B, estimate this derivative using the average rate of change over this interval. Okay, so the average rate of change, okay, is basically the slope of the secant on those two things, which means I need to find f of a negative 0.9 minus f of a negative 1.1 over a negative 0.9 minus a negative 1.1. That is the slope of a secant. And then we can use your calculator and work these out and get some numbers here. I have these numbers already. I'm going to go ahead and just write them for the sake of time. And then down here would be 0.2. And then as you work this out, you're going to get a negative 0.4 over 0.2, which is a negative 2. That is interesting. I'm going to give you a little note here. That usually does not happen. This is just a coincidence. Okay? It's just a coincidence that it actually became exactly the same number. That's kind of like unusual. Usually it'd be something close to negative 2, okay? But it's almost never exactly the same as the actual derivative thing. And the last one is to use the power rule to find this value. So here's how we would do that. The first thing you can do is find the derivative of this function, with respect to x. So f prime of x is equal to 2 times x, lower the power by 1, so 2 minus 1 is 1, times dx dx, which is going to become a 1. So you literally just get 2x. Okay? So once I have that, then what is f prime of negative 1? Well, just plug it in. 2 times negative 1 is negative 2. And so you can see that this approach is a lot easier to do and quicker. Okay? So let's take a look at the next thing I have here. So there is our stuff again. Pause right here if you want to write all that out again, if you might move the other paper too soon. Note, the power rule, or any derivative rule, in most cases is the most efficient way to calculate the derivative at a point. This is not the same as being the best way. The best way always depends on the information that you are given. So you need to be prepared, based off the information given, to use one of these methodologies for helping you find a derivative at a point, whether it is a limit definition approach, an approximation approach, or a rule approach. That's what you need to be aware of, okay? For any derivative rule. So another rule we have is the constant rule. Okay, constant multiplier. So if f equals some constant times some function, okay, where u is a differentiable function of x, then literally the constant can just be moved out to the front. So you can kind of like just bring it to the front and then take the derivative of the function itself. Okay? Basically, I have here the coefficient just comes along for the ride. So I think I have some examples here that we can walk through and show you how that works. Okay? So here we go. We're going to find the derivative of this one right here. So this is a y, so I can write it as dy dx, because the variable is x. This is a constant right here. So literally it can come out in front, and then I'm going to take the derivative of just this part. So the derivative of x squared is 2 times x, lower the power by 1, and then times dx dx. That is how you would do this derivative, using the constant rule. Just take the constant, move it to the front, and times it by whatever the derivative is of the remaining function. Then you can come through here and clean this up by just multiplying this out. This is not distributive, this is just a multiplication. So it's going to be a negative 32 times x, and dx is just 1. So that would be my answer right there. For this one right here, again, we have a y, so I can use dy dx. This is 100. This is pi. This is just a constant. Okay? This is just a constant. So the derivative of a constant is 0. We're done. There it is. There was no x values in there. There's no function, so it was just a constant itself. All right, this one over here, you might want to rewrite any radicals into exponent form. So this is going to be rewritten as 24 x to the, this is a 1/3 power, this is a 2, so this is x to the 2/3. That is y. So dy dx is going to be 24, that's the constant, and then take the derivative of that, which is 2/3 x, lower this by 1, so 2/3 minus 3/3 is a negative 1/3 times the derivative of x with respect to x, and then we can multiply this stuff out. So 3 goes into 24, 8, 8 times 2 is 16, and x to the negative 1/3, and you can be done there. Okay, this one right here, last one, 4/3 pi x to the third. Remember, all of that is a constant. So dy dx is the constant times the derivative of that expression right there, which is exponent in front, lower the exponent by 1, dx dx, because that's the variable. As I clean this up, these 3's drop out. I'm left with 4 times pi times x squared, and that is dy dx. Okay? Let's look at another rule. This is the sum and difference rule. What this one is basically saying is here are 2 functions of x that are differentiable, and I'm adding the pieces together. So I'm adding these 2 things or subtracting the same thing. It's telling me that I can take the derivative of each individual piece. Now, why would I want to be able to do that? What's the importance of that one? Well, you will see that I can now take the derivative of something that looks like this. So I have these examples over here. We're going to just do them on the side here to walk you through how that rule is used. So here we go. Notice we have basically terms. We can take, instead of taking the derivative of the whole entire thing in one fell swoop, we take a derivative of each individual piece. Okay? In this problem right here, even though it's not saying so, this variable is t. That means any letter that is not a t is considered to be a constant. Okay, so keep that in mind. So the variable is t. Any variable over here, any letter that is not a t, is a constant, and it is treated as such. So what is h prime of t going to be? Well, over here, that would be the constant, so it's going to be 1/2 t times, now take the derivative of this piece, 2t dt dt plus, now we do this term. B is a constant, and so what is the derivative of t? It's just 1. And then dt dt. And the last one over here, what's the derivative of this? Well, this is a constant, so its derivative is 0. So as I clean all these things up, I get h prime of t. This 2 and this 2 will reduce. I got g times t. That becomes a 1. Plus, that's a 1, that's a 1, so it'll be plus v. And that is your derivative. When I look at this function right here, I notice that I have a radical over here. So the first thing you should do anytime you have a radical is to always put it in exponent form. So just rewrite the problem and put all radicals into exponent form. This is a square root, this is a power 3, this is 3 over 2. Okay, now I can take the derivative. G prime of x, 1.2 is a constant, so that would be 0. This is just a constant times x, so it's going to be 15 times the derivative of x is 1 times dx dx minus Constant is 8. Take the derivative of this power rule right here, so it'll be 3 over 2. X, lower the power by 1. So that gives me 1/2. And then times dx dx. And then we just go through now and clean all this up. Make it look pretty. 0 is gone. This is just a 15. 2 goes in 8 4 times. Times 3 is 12. X to the 1/2, and that's a 1. And that is my derivative. So you can see that these become very simple, if you learn how to do them, and we don't have to do the limit definition all the time. What should we do with something like this? Okay. Well, we have rules for stuff like this, but the first thing you should look at is, can I simplify this? Can I rewrite this in a way that makes it easier to do? This is a single term on the bottom, which means I can divide this term into every one of the terms on top. So y can become 3x to the 5th. I'll show you this all the way through this time. This is 2x over x squared. This is 7 over x squared. So as I clean these up and simplify these things out, this first one becomes 3x to the 3rd. This becomes 2 over x, and this becomes 7 over x squared. So I can look at it from that perspective right there, and then I can make them all into power rules. This would be 2x to the negative 1, 7x to the negative 2. And so this is how I want to look at y. So this is this, and this is easier to take the derivative of. So dy dx equals the constant times the derivative of x to the 3rd, which would be 3 times x, lower the power by 1, dx dx. The next term is the constant out in front times the derivative of this quantity, negative 1 times x, lower the power by 1, dx dx. And then the next one would be minus the constant out in front times the derivative of that quantity, negative 2, lower the power by 1, dx dx. That's how you go through the derivative stuff. Now go back through and clean it all up. 3 times 3 is 9, x squared, dx dx is 1. Negative 1 times 2, negative 2, x to the negative 2 times 1. Negative 2 times negative 7 is positive 14. X to the negative 3 times 1. And there it is. You can leave it just like that. Okay? Sometimes they're going to use the derivatives. Okay? So you have to understand your knowledge and understanding of the derivative to help you find stuff. So this is a twist on what we were just doing. Instead of just finding the derivative directly, they're going to ask you to find a missing value. So there is a k in here. What is that number? If I give you all this information, what would that number there become? Okay? So when you look at something like this, you ask the question, all right, well, this is an h, and I look at my table over here, and I got a lot of derivatives. Well, that indicates to me that I must take the derivative of this. So we have to use our derivative rules for this. I look at this right here, and very clearly I see I have a radical. Always look for those first and those fractions that I can then rewrite into power rules. So h of x, I'm just rewriting this. This is 3 times x times f of x. This is 8 times x to the 1/2 plus g of x. Okay? So I want to rewrite it in that fashion. Now I'm going to take its derivative. What is the derivative of h with respect to x? It's the constant, so it's the constant times the derivative of that function with respect to x, which is f prime of x, minus the constant times the derivative of that function, which is 1/2 x, and then lower the power by 1, dx dx. Sorry, should have been a dx dx in here too. Sorry, my fault. And then the last one is the derivative of that, which is g prime of x. And the variable was x, so we have a dx again. So as I look at this, I have a 3k f prime of x minus 4x to the negative 1/2 plus g prime of x. Okay? X is 16. So h prime of 16, okay, is 3 times k times f prime of 16 minus 4 times 16 to the negative 1/2 plus g prime at 16. Now I have numbers in my table. What is h prime at 16? Pi 3 times k times this, which is 4/3. This is 4 times, now what is this going to be? Well, if you can't see what this is over here, remember this, the 1/2 is a square root, and then negative puts it on the bottom. So this is going to be 1 over the square root of 16, which is 4. And you can take that off to the side and take a look at it if you need to. And what is g prime at 16? Negative 10. Okay, so let's clean this all up. So I have pi, these 3's reduced, gives me 4k. These things reduced gives me a minus 1, then a minus 10. So as I solve for k right here, I'm going to get, and you can do all the numerical numbers and move things around, pi plus 11 divided by 4. And there's k. Okay, so once you know the rules, you can use them in many fashions. So it's not always going to be just a straight direct. Sometimes you have to go around using symbolic notation, stuff like that from this kind of information. So be aware that this can occur. Okay. I have another thing I want to show you, another rule. This one is the product rule. This is one of your big ones. I have two functions that are differentiable with respect to x, u, and v. What if they are multiplied together? Okay, so there's a little rule right here. Here's how I remember it. This is the first function. This is the second function. So it is the first function times the derivative of the second plus the second function times the derivative of the first. Say that little phrase in your mind. Every time you use it, you'll have it memorized. It is the first times the derivative of the second plus the second times the derivative of the first. Every time I do one of these derivatives, that's what I say in my mind. So here is a function we're going to do using this rule. So I have h is equal to the product of these two functions that are differentiable with x. What is h prime at x? So h prime of x is, this is the first, this is the second. It is the first times the derivative of the second. So now I take the derivative of this quantity. This is a constant times x, so this will be 8 dx. And the derivative of a constant is 0, so that'd be just 0. First times the derivative of the second. Plus, this is now the second, times the derivative of the first. This one here is a constant times, and I'll take the derivative of x squared, which is 2 times x times dx minus the derivative of the constant, which is 0. So we go back through here and clean these up. This is a 0, this is a 1, this is 8 times this quantity. I'm not going to multiply it all out. I'm just going to write it out by cleaning it up. Over here, that's 0, that's a 1. This is 10x times that quantity. Right there. Okay. And then if you wanted to, you can multiply everything out and combine them all up in like terms, and we can do that. So this right here becomes 40x squared minus 16 plus 80x squared plus 30x. And then you would just write it all in proper order. And you end up with 120x squared plus 30x minus 16. And there you go. Now, this is simple enough that I could have, if I wanted to, multiplied this out first and then took the derivative, and I would have gotten the same thing. Okay? So let me go ahead and show you this right here so you can kind of see what some side notes that I wrote about this. You can distribute the two binomials and then find the derivative, but for larger polynomials, this can take too long. Okay, these are small and simple, but if they were longer, you wouldn't want to do that. On the AP exam free response, if they ask you to find a derivative like this, you do not need to go all the way to here. Although this is the simplified version of the derivative, this line right there is the derivative, and you can stop. Okay, you do not have to simplify. Once you have found the derivative, that's all I have to do is to find that derivative. Once you have found it using the process, you do not need to simplify it. But that's on the AP exam. We will talk more about that as we move along. Okay, so I have some more examples we're going to look at. A couple more to go. Here's another product rule example. So here is a function g. Find g prime at 2. Okay, so we're going to go a little bit less stuff in here. So we know that every time I do this, I'm going to put a dx. So, and they're always going to turn into 1. So if the variable matches what I'm taking respect to, I'm not going to write that anymore. I will say it, but I'm not going to write it. So I have the first times the derivative of the second. So what is the derivative of this now? And I always put the derivative I'm doing in a square bracket so I can come back later and kind of examine my work to see where mistakes may have lied. There's going to be a 2 times this derivative, and that 3 is going to go out in front and end up multiplying to this. So I'm going to take the 3 times the 2 and put it 6. I'm going to lower the power by 1, dx, and the derivative of the constant is 0, so it's going to be plus 0, so I'm not going to write that either. And there's that. First times the second, here's the second, times the derivative of the first, 4 times x. So basically what I'm asking is, what's the slope of a line with the slope of 4? Right? This is a slope, this is a line. What's the slope of this line? That's what I'm asking. Well, it's mx plus b, so the slope is 4, so this is just simply a 4. Now, at this point, you can do two things. You can simplify this expression out and get the expression, depending, again, on what you're asked to do. But all I ask you to do is find out what this was at 2. I don't need to simplify this. All I have to do is really just plug in the 2. So if I go through this whole entire expression right here, replacing all the x's with a 2, like so, times 4, then I can just simplify it with the numbers and get my answer that way. So you can go through all this right here. Basically, it boils down to is g prime of 2. I got it to be 260, so make sure I have the right, I do the right arithmetic to get that answer, okay? Now, this example right here is different. Here I have an expression on top and on the bottom. We need a new rule for this, and that rule is called the quotient rule. Okay, this is another big one you're going to use a lot. Again, the two functions that are being divided. I have it this way. The bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom square. So it's just simply using that little process, that little rule. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. Just remember that mantra every single time. Every time you use it, say that mantra, and it will help you memorize the rule properly. So let's look at an example. This is the last example. So here's the bottom, here's the top. G prime of x is the bottom times the derivative of the top. The derivative of the top is going to be 2 times 5, which is 10. Lower the power by 1. The derivative of the constant is 0. That's my derivative, dx dx. The bottom times the derivative of the top minus the top. Notice I am putting parentheses. Every time you do something, put it in parentheses. The derivative of the bottom is just going to be an a all over the bottom squared. So again, that is the derivative. You want to simplify this as much as possible for classroom purposes. If I only asked you to do this for the AP exam, this is where you would stop, unless they told you to do something different. You can clean up the top, and then you want to get 80x squared minus 30x. Over here, I'm going to get a negative 40x squared minus 16. I am not going to multiply out the bottom. There is no need. The only purpose, the reason I'm doing this is to see whether or not I might have a possibility of maybe factoring or reducing. Okay? Cleaning up the top up here, you're going to get 40x squared minus 30x minus 16, and then 8x minus 3. And there's no factor of the top that's going to match this one down here. And how do I know that? Because 16 does not have a 3 involved. Remember, this number comes from multiplying these back numbers. And 3 does not go into 16 in any fashion, so there's no way it's going to factor anymore. So this is your g prime of x, and you can be done right there. Okay, so this is the different rules. You want to study those. You want to memorize those as soon as possible. The sooner you know them, the better off you will be. And let me put this up here so you can copy that down, last example down. Always put use parentheses for the numerator and denominator, things like that. If you have any questions, make sure you ask, and we'll be doing a lot of practice. So that ends the first video.